Okay, here we go. This is paper 4.2 and question 5. It's almost a space simulation. We're looking at how craters form when a ball, so in the sense of maybe an asteroid, lands on a soft surface. Okay, as ever, please try the question first before you listen to me explain this wonderful answer. Okay, so we've got the assembled apparatus and you're told the procedure, which is nice. Okay, we make this level, the surface level, lots of typing here, right? Lots of information here. To be honest, do you need to read this? I don't know. I mean, I glance over it. I think in an exam, I would take time just to make sure you understand the experiment before you move on. Okay. We then have this. This is the important bit. We've got the crater. Okay. Now you notice this is a non-perfect crater. That is going to come up later. Crater later. Okay. We repeat the procedure for 4 other heights above the sand. So let's find out what we do. Okay. We measure firstly the height of the ball above the sand. Fig 4 shows the ball just before it's dropped, and we've got the height of the bottom of the ball. Okay. Now again, this comes into just reading the question. I've just recorded a video where you measure the center of the ball. This time we're measuring the center of a pendulum. This time we're measuring the bottom of the ball. Okay. So all we're doing is measuring to the nearest 0.1 centimeters. Okay. Again, I've drawn a little line. That's going to be tangent to the bottom, 17.6 centimeters. Okay, so that's, you get a mark there just for reading a ruler. Now the thing I worry about, the only thing I worry about this is students making sure that they read the correct thing, and the bit that's going to be difficult is where it lines up with, say, 17. If this was lined up with 17, you would need to write 17.0. There is a difference, okay? 17.0 is different to 17. Have they written here? No. All of these are given to the nearest 0.1, okay? Just make sure that you are giving it, if you have a 17, 17.0, 22, 22.0, okay? Now I've got my number 37 here. That's been filled in from another question, so let's just go here. Aha! Now, I reckon I might have made a mistake here, because I remember looking at the mark scheme for this one. I found this one really hard to read. Okay, so I tried to measure the diameter of the crater. And yeah, I think when I read this, I read the left-hand side is 9.1. I looked at the mark scheme and said 9.2. And I'm trying to ask myself whether I would lose marks here. Maybe. And I don't really know why. I did find this really hard to read. But I suppose just take your time. Okay, it should land on one particular division. Okay, so when the markers did this, they said 9.2. I kind of disagree with it, but we'll just go with it. Okay, we won't lose out any sleep. The process is still the same. What we're going to do is calculate the diameter. No, regardless of what you've written here, you still get a mark for firstly turning it into, finding out your diameter and then converting it into millimeters. Okay, and that's what you need to put into your table. So this could be a 38. Don't worry about it. Okay, so we then have the question here. Now I've noticed this has come up again and again in the most recent papers. So I really encourage students to try the most recent papers in this respect. Okay, it says state the relationship between the height and the ball and the diameter of the crater. So I'm jumping around a lot. Let's look at the data. All right, now for this, please do not overthink it. Overthinking will get you in trouble here. A lot of students will talk about proportionality, inverse, direct, these kind of things. All this data tells me is that higher the height, the higher the diameter. And so that's all you have to write down. Just write down the higher the height. As height increases, the diameter of the crater increases. Okay, do not try and get directly proportional in here. That could come later. They might ask you to test whether it is directly proportional, and we'll talk about that later. Now, one possible error in this investigation is that the meter rule is not placed perpendicular to the surface of the sand. Name one suitable piece of equipment it allows to show if the meter rule is perpendicular. I'm really glad this has come up because I don't think this is one that students will know. You can use something here called a set square. Now, a set square, I've tried to draw it here, is a sort of triangular ruler. It's fixed at 90 degrees to make sure that the vertical and the horizontal are at right angles to each other. It's a nice piece of kit, okay. Haven't seen it in many labs. pretty old-fashioned. Okay, so you could also use a protractor. That would be fine as well. You could imagine a protractor put in position to measure the angle to make sure it's 90. I'd imagine more students would be familiar with this. However, this is one that comes up. The set square is this kind of triangular thing that you place on the table. Okay, another source of error. Right. Well, for this one, again, there's various things you could do, but the one that I've chosen was this one, which was the variety of the diameter. You notice that the crater was not smooth. It's not a circle. It's kind of a wobbly, unclear circle. So therefore, you're going to get a variety of diameters. If you measure in the diameter in one particular position, you are going to get different values. So a suggestion for an improvement or to reduce that would be to measure at multiple points. All right. Now, key here, don't just write down measure at multiple points. Write down measure at multiple points and calculate an average. Anytime you repeat anything, CIE particularly enjoys to see the idea of calculating an average because it shows that you're thinking about it a little bit more. It's not just that you measure it again. Why bother measuring it again if you're just going to get a different number all the time? We're going to take that and we're going to try and measure it so that we get an average value. Okay, that will eliminate the effect of our uncertainties on our data and allow us to identify anomalies as well. Okay, all right. Here's a good one. I think I said this in a previous video. Sometimes we can overthink these things. Suggest one reason why the tray containing the sand is not made of glass. Now, there's so many different things you could write here. Might be too heavy. Yeah. I mean, the really obvious one is that it could smash. Okay, the ball landing into that thing, this metal ball or whatever type of material it is landing on there, could crack your tray and then therefore cause this thing to smash, all right, or to crack, and it would therefore present a safety hazard. Now, I'm pretty sure when I read the answer to the mark scheme to this, it just said it would smash or crack. Give a bit more in there. Why not? Why is that a problem that it smashes? Well, it's a safety hazard. It could cut you. Okay, it's not a safe thing for you to be doing. Seems obvious, but students may have missed that. You never know. Okay. Now here we go with another student repeating the investigation, okay, and the table showing some more results. Okay, oh yes, I've got to apologize about this one. Okay, ignore my circles here. I'll talk to that in a second. First thing we've got to do is calculate the average diameter of the crater for the 40.0. You notice all these heights are given to 0.0. That is because they've been measured by a ruler with the smallest dimension, which is 1 millimeter or 0.1 centimeters. All I'm going to do here is I'm going to take for the 40.0, 22 plus 24 plus 24. Now, that's going to give me, if I got my maths correct, 70. 70 over 3 is 22.67. However, we're given all of our answers to two significant figures here. So we're going to ignore that decimal and just give the answer to a whole millimeter. 22.67 is going to be 23. Okay, so make sure you give your answer there to an appropriate value, no extra data. This is where I've screwed up here. Okay, one of the calculated averages is incorrect because an anomalous value is used. Okay. Okay, so we've got anomalous values used in the calculation. Circle the incorrect average diameter, and this is where I circled the wrong things. All right, what I meant to circle was this one. This is the incorrect average diameter. All right. Now, why? If we look at the data, yeah, we've got a 41 and a 42 and a 40. They're very close together. We've got 27. We've got 27, a 37, and a 32. All right. That 27 is very far away from these guys. Okay. And then we've got our 27, 30, and 28, and these guys all close together. Okay. So it's included an outlier in the calculation, right? They've made a mistake. Yeah. And they've included the outlier in their calculation. What they then need to do is to then go and repeat their data taking and find out which of those is the outlier and then eliminate it from their average calculation. Okay, last one. The student investigates the effect of volume V on the diameter of the crater formed. Okay. It then asks us, you're given the radius and you're asked to calculate the volume of the ball. You're given an equation. Okay. We're told the radius, we're given the volume, 4.2 times r cubed. okay, which gives you a 33.6, and we're going to put that one in here. Okay, all pretty nice so far. Noticing we're going to give to 1 decimal place, where this one's also given to 1 decimal place. This is the bit where we get to proportionality. So CIE does not expect you to kind of justify proportionality until it kind of claims it either way. So in this says, the student concludes that the volume is proportional to the diameter of the crater. Okay, is proportional to the diameter of our crater in this case. Okay. So we want to state if they're correct. Now the answer here is no. Now, how do we know that? If it was proportional, then what we'd be looking for is doubling the values. So if I go from here, you notice here we've got 16.8. Okay, we're going to double to 33.6. We've taken the volume and we've doubled it. Now, what we then have to do is check whether this will double. You notice here that 37 doubled makes 74. It does not double to make 62. Okay, so what you're expecting to write down here is something to that effect, which is that when the volume of the ball doubles, all right, the diameter of the crater does not double. If we are looking for a proportional relationship, then we are waiting for the fact that the two quantities will double together. Okay, if it's inverse, then one doubles, the other one halves. However, if it is directly proportional, then these guys are going to double together. Okay, and in this case, we do not double, and so therefore that's what we do. Now, another way of doing that is to calculate the ratio. We calculate the ratio of the volumes and then the ratio of the diameters. Those ratios should be equal, and in this case they're not, so therefore they're not proportional.